Here we go. All right, yeah, so how many? 10, right? So this is C4H10. Your isomer must also be C4H10. There's only one answer. I take one of these carbons that's on the end, or the beginning, and I'm going to put it right here. So if I take this one, and I put it off of the second carbon as a branch, now that's 2-methylpropane. This is butane. These are isomers. They're both alkanes, both saturated, both C4H10. But what is an isomer? Same number of atoms, same formula, different structure. So I just wanted to review that with you. Let's go over the homework now. All right. So back to the front. I'm going to skip 1, 2, and 3 just because if you can do 4, 5, 6, 7, 1, 2, and 3 are easy. So I'm going to skip 1, 2, and 3. I'm going to go over 4, 5, 6, 7. And for the sake of time, I'm just going to bang these out real quick on the board. So stay with me. Here we go. Number 4, 4-methyl-1-pentene. All right. So number 4, we got 1, 2, 3, 4, 5. Why 5? Pent. 1-pentene means the double bonds on the first carbon. 1, 2, 3, 4 has a methyl group. Now I have to add all my bonds. Now, big mistake a lot of kids make. Eyes up here. They get the carbon backbone, they get the carbon structure, and then they say, oh, I got to put in my bonds for the hydrogens, and they just start putting them all over the place. What's wrong with that? Only 4 bonds per carbon. This one already has 2. 1, 2, 3, 4. I can't put one here. If I do, it's wrong. 1, 2, 3. I can only put one more bond, up or down. I can't put 2. Kids who go fast, just put them all over. Just be careful with that. So 4 bonds per carbon. So there's number 4. Number 5, 3-ethyl-2-pentene. 1, 2, 3, 4, 5. Now the double bonds on the second carbon because it's 2-pentene. This is 1, this is 2. The third carbon, 1, 2, 3, has 2 carbons coming down. That's ethyl. Now again, all the bonds for the hydrogens. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. No hydrogens on this carbon. It already has 4 bonds. 2 here, 3 here, 2 here, and 3 there.
Is propyl a thing?
Propyl is a thing. It's got to be a pretty long chain
For it to
yeah. But yes, it is. There's all types of. There's that book, that big fat book I showed you, the organic stuff. There's probably, I don't know, off the top of my head, maybe like 10, no, 20 different types of substituents that pop up, but it gets more complicated. But yeah, good question. Where am I? 6. All right, 3-ethyl-2-methyl-2-pentene. 1, 2, 3, 4, 5. Again, double bond on the second carbon. That's 2-pentene, just like this. Now we have 3-ethyl, 1, 2, 3. Here's my ethyl, and then 2-methyl. So second carbon has a methyl coming off. So there's all my carbons for number 6. And again, I got to put my bonds, 1, 2, 3, 4. 1, 2, so no hydrogens here. 2 here, 3 here. And there we go. There's number 6. Number 7. We got 1, 2, 3, 4, 5, 6. 1, 2, 3. There's my 3-hexene. Hex means 6. 5, 5 dimethyl. So 1, 2, 3, 4, 5. There's 2 methyls, one going up, one going down. That's 5, 5 dimethyl. 3-hexene. Put on all my bonds. 1, 2, 3, 4. 1, 2, 3, 4. And that's how we do it. So I'm going to move on. If you have any questions, I'm hoping lab will kind of fix all that because they're doing a lot of this in lab. So the lab is really useful for this topic. So yeah, it's good to have homework and go over it. I'll show you the answers, but I'm not going to spend a ton of time because that's what lab is for. All right. 8. Oh, who's going to be? Renee, what do you think? 3-ethyl-1-pentene. Very good. It's very similar to this. This is 3-ethyl-2-pentene. It's just the double bond is here. So number 8 and this are almost the same except the double bond's here. By the way, that is an isomer. If you move the double bond, it's not exactly the same thing. The name changes. So this and number 8 are isomers. Same number of atoms. The bond just moved over. So So those will be called isomers. All right. Now 5, 6, 7, 8. All right. I'll go over 2 of them. Which 2 you want me to go over? I'll give you all the answers, but I'll go over 2 slower. Which 2?
7.
7. And? Bueller?
8.
Thanks, Red. 7 and 8. All right, here's how I would do this. How many carbons are in number 7?
9.
9. So I would just do this. 1, 2, 3, 4, 5, 6, 7, 8, 9. I would put on all my hydrogens, and what would that be called? 9 carbons. Nonene. Nonene. Yeah. 9 carbons in a straight chain. That would be C9H20. 3,3-dimethylheptane is C9H20. Why? They're both alkanes, both saturated. That would be an isomer of number 7. You guys may have something different. It's really hard to kind of go over every single possibility here, but that's the easiest way. If they give you a structure with branches, just make it a straight chain. Well, that's number 7. Number 8, I would do the exact same thing. How many carbons in number 8? 7. 3, 4, 5, 6, 7. 1 pentene. I would keep the 1 pentene, and I would just put it all in a straight chain. I would take that ethyl, and I would put it in the chain, so that would be 1 heptene. 1 heptene. That's an isomer of number 8. Okay, number 5, an isomer of butane. 1, 2, 3. This is what we just did as the warm-up. Now, what Tyler said yesterday, eyes up here. If you drew this, that's wrong. That's still butane. That is still connected. So that is the same thing as this. You're just taking the carbon and bending it. And remember that. I'm glad you asked that yesterday, Tyler. It's a really good point. This is the only isomer for number 5. We just did that as the warm-up. And then number 6, hexane. 1, 2, 3, 4, 5. You could take that 6th one and put it anywhere you want here. If you put it here, that would be an isomer of hexane. There's multiple ways to do that, but that's just one example. Just rearrange it. It's still C6H14. So, would you say you have a decent grasp on isomers?
Yes. Yeah.
Tomorrow or the next day, I'll do some warm-ups. I'll do another one. I'll have you practice, need me the whiteboard, throw in isomers, so that'll help. All right, take out your notes. Take out table R, please. Table R, the pirate's favorite chart. No? Nothing?
Really bad.
Wait, could you repeat that?
Table R is the pirate's favorite chart. R.
Do better than that.
Yeah.
Maybe not.
Whereas,
All right. Now, good. Got time. Before I teach you about table R, stop. In lab, who remembers the graph we made? What's the y and the x-axis?
Y is grams per mole, pretty sure.
Try again.
It's
Boiling point, molecular weight. What do the graphs look like? They kind of like do something like this, right? Kind of.
No, the other one, the one starts farther up and ends further.
Okay.
I don't know,
But
I didn't do it yet.
they're both going up, right?
Yeah. Yeah.
Okay, now, eyes up here. You don't have to actually put this in your notes. I'm just, because I don't have both labs, it's easier to talk to the classes, because I have everybody. What does this graph show? Corey, what does this show? As molecular weight. Good. Yeah, as the weight of these things, these molecules, right? So if I have 2 carbons versus, what is that? 6 carbons, this is going to weigh more, right? Have a larger mass. So this I would expect to have a higher boiling point than this. That's what this is supposed to kind of teach us or show us in lab. And what kind of relationship is that? Direct, right. So I think the lowest was 16, right? CH4? Yeah. And the highest was, I don't know, 80 something? 82, anyway? 84? Okay. And then, if we bring these down here, negative 161, and then the highest was like 30 something, maybe 30, I don't know. It doesn't have to be exact. But you go from negative 161 up to positive 30 degrees, so it's a pretty big change. As you add carbon, so if you have, again, ethane or hexane, if you compare these and you look their boiling points up online, this is going to be significantly higher. And that's what this is showing. The more carbons that the chain contains, the higher the boiling point. Why? Why the bigger these things are, the harder it is to boil? Why? Anyone have an answer?
Particles.
More particles, good. Something else. What's the only thing that dictates boiling points, freezing points, density? Close. Forces of attraction. So, if hexane has a high boiling point and ethane has a low boiling point, between ethane and hexane, in terms of forces of attraction, explain the trend. And you would say hexane has greater forces of attraction. Next question.
Why though?
Why?
Ligative properties.
That's solutions, but good try. Why does hexane have a higher, greater forces of attraction?
There's more particles. It's like carbon.
More
More particles, what?
Pulling at each other.
Attracted to each other, yes, exactly. Okay, this is why.
friction.
What did I use this
Heat.
analogy for in the past?
Energy. Touching.
Surface area.
Surface area, yes. If you have a little tiny molecule, there's not much surface area. That's like fingertips. But if you have a longer, bigger molecule, like palms touching, okay? So think about if I bring another hexane up here underneath it. So I have 6 carbons next to 6 carbons. There's going to be a lot of interaction between them. If I only have 2 carbons interacting, that's literally less particles, less forces. So the longer these chains get, the more forces there are because there's more surface area. Hopefully that makes sense to you. Now, what about this? So again, you're not writing this down, just watch. Pay attention. Get ready to answer questions. Alright, now, so you got the top one, how many carbons? 5. Bottom one? 5. They're both C5H12. They're both alkanes. This one has a higher boiling point. So, what I just taught you now, throw it out the window. This is true. This is true. This is something I want you to understand. The bigger it is, the stronger the force is, more surface area, higher boiling. Everything we just talked about is true. But what about if they had the same weight? They're both C5H12. Why would this one have
different density?
that? Actually that has something to do with it.
It's in a more favorable position.
It is for what?
Bonding.
Attraction. It's all about force of attraction. The boiling points properties are all about force of attraction. Okay, ready? Here we go. Aha. Who's that from? That's from something.
I don't remember.
What was that foolish thing you wanted me to do yesterday?
Me?
The
The
wall.
wall.
Oh, yeah, the wall.
Yeah.
Do it real quick.
Okay.
Plus the wall right there.
Nope. Alright, we have a ping pong
I'll
ball.
toss it to you.
I'll slap it down. Alright, now, here's a ping pong ball. Here's a marker. Now, if you were going to relate these 2 molecules to these shapes, which one would be which one?
The marker
Marker
is top.
would be the
Marker
top.
would be the top one, and the ball would be the bottom. If I was to kind of trace this, sort of, right? This kind of looks like a ball, spherical. This kind of looks like more of a straight line. Okay. Why does this boil at a higher temperature than this? More surface area. If I bring another one of these up to it, there's a lot of contact for the forces to interact. But if I bring 2 ping pong balls together, there's only a little tiny space, little tiny spot they actually contact each other. So two spheres, and I've done this before with you guys, with this versus this, if you remember, but this, not much surface area. This, lots of surface area, okay? And I think we talked about geckos climbing up windows and stuff. Like, they're hydrogen bonding on they have like these little hairs on their feet and hands, feet, whatever.
They should set them on the ceiling.
Ceiling too, right? Because they have a lot of surface area. They don't walk around like this. Their hands are like this, or their feet, whatever you call them. They want more surface area so they can adhere or attract to the walls. Yeah,
Which one did you say had higher boiling point?
this one,
Why?
more surface area.
Wouldn't that make it
Yeah,
lower?
wouldn't that make
because
it
would
lower
transfer
because it's got more
faster?
surface area?
Whoa, you guys are regressing on me right now. Okay,
But that
forces of attraction keep these particles close together. When you boil, what do?
Separate.
Right. So if you have strong forces, it takes a lot of energy to separate it.
Yeah, but why were you talking about surface area then? Because you're confusing us. The more surface area doesn't even.
The higher the forces, the more surface area.
I thought it was the more surface area, the faster it boiled.
No,
Because there's more water.
Particles being
You
in
never
contact
said
with
those.
the heat.
no,
Yeah.
no. I said the opposite.
Yeah, I was like,
So up here, these particles. So let's make sure we got whatever we all thought. Let's make sure we got straight. Up here, the bigger these molecules are, the more surface area they have, the harder it is to separate, the more energy it takes to boil. The ones that are spherical or little tiny particles, they have low or weak forces, meaning it's very easy to boil.
But what we're trying to say is, if they were kept on, they're like this,
Sure.
wouldn't it be a lot easier to transfer the heat to go through instead of they're all balls?
So transferring energy is a little different than what I'm saying. So if you want to go from a liquid state to a vapor state, if these particles are really attracted to each other, it's going to be difficult to get them to separate into a vapor because they are very attracted to each other. Here, since these have hardly any attraction between them, it's very easy to separate them. So transferring energy is not really what I'm talking about. I'm talking about how much energy does it take to separate them from each other. So these having low surface area, not a lot of attraction, very easy to separate. These, a lot of surface area, very hard to separate. That's why the boiling point's high.
Did you get this?
Wouldn't that be some
Yeah.
I get what you're saying, but everyone else is
Because
contradicting.
they were treating those as they're going to be separating, but those are individual
Wouldn't that make the
particles
boiling
connected to other
Particles.
Right now I'm confused.
If you have, so something we've been focusing on all year, higher forces, higher boiling point. Stronger forces, stronger boiling point. There's nothing different here, it's the exact same thing. I'm just applying it to organic chemistry. So like water boils at 100 degrees Celsius, ethane boils at negative 88. Because ethane has really weak forces where water has really strong forces. So what's the confusion?
But, because you keep on saying surface area, so, but when you said if you spread water out, it vaporizes faster.
Yes.
So, that would be the boiling point.
Okay,
would be
alright.
lower.
So here's the thing. So the boiling point of, let's say, water, it's 100 degrees Celsius. So if I have water in this water bottle here and I let it sit here, it will evaporate. But it will evaporate faster if I dump it on the floor and you have more surface area, so more particles are exposed to evaporate.
But
The boiling point is still 100 degrees.
I know, but I'm saying if you were boiling it,
Yeah.
if you were boiling water in that,
In
it
this.
would take longer than if you were boiling on a
Right,
flat.
but the temperature would still be the same.
Yes.
That's what I'm trying to. I'm just comparing the temperature of this one boiling and this one. More surface area. So you're relating surface area to rate of evaporation. I'm relating surface area to contact of particles inside the substance itself.
Okay, that
Tyler's
I get
doing
that.
it.
Yeah, I get that.
You
ever seen that episode of SpongeBob where
So, no, these are. I'm glad you guys asked the questions.
So I'm thinking, like the long one, it's kind of like Legos. They go like fit real close together.
Yeah.
But like the condensed one, it's kind of like a bucket full of like ping pong balls. There's more space in between them.
Yes.
So the forces are weaker.
Yeah, that's good actually. Yeah, I like what Quinn said. So if you take a bunch of Legos and just stack them on top of each other, they fit very nicely in there. They fit very tight. But if you have a bucket full of ping pong balls, there's lots of spaces in there, and those spaces mean they're not held together as tightly. Yes. Yeah. That's exactly what I'm going for. So
Okay.
hopefully we're on the same page now. I might have to go through that again tomorrow, and that's fine. Now, you're still gonna have homework, so give me 2 minutes here, or a minute. Go to table R and take out your homework. Let me do number 1 with you.
Take my life.
Let me do number 1 with you, so you know what's going on.
This one?
Yep. So you're going to use table R, and you're going to look at the homework on each problem, and you're going to tell me what functional group is in that molecule. How do you do that? Well, if you go to table R, look under the functional group column, you see all these symbols. FCl, BRI, you see an OH, you see an O, a C double bond, O with an H. So you can see those functional groups. If you see them in the carbon chain, then that's the functional group. So for example, number 1, I see an OH. Now I go to table R, who has an OH?
Alcohol.
Alcohol. So everyone write alcohol on number 1. Let's see if we have time to do number 2 together. So if you go to number 2, this one's a little bit challenging, but I see, forget number 2 for a second. Go to number 4. What functional group does number 4 have? It has to match
Double
exactly
bonds
what's
without.
in the box.
None.
It's not ketone. It's not ether.
Ester.
Not an ester.
Is it
It's an
aldehyde?
aldehyde. Number 4 is an aldehyde. It has a C double bond O with an H.
Okay,
I only have an
can you do number 2?
Yeah, can you do
Number
2?
All right, yeah. So, yeah, I was kind of a jerk on some of these. Number 2. Hey, I'm glad you came to school today. Number 2.
She was here yesterday.
Yeah, she came in late. Number 2, I believe, is a ketone.
You believe?
Well, I'd have to draw it out. I'm trying to do it quick.
So how are we supposed to
Yeah, how are we
figure
supposed to
these
figure it out?
Yeah.
So, okay.
I
So
don't understand that.
Why are you doing this to us?
Because if I don't understand, I'm
So-
just guessing.
the way you're supposed to do the ones that I didn't draw is draw it out and figure it out.
Oh,
Seriously?
yeah, I'll figure it out. That's great.
Do the best you can. We ran out of time. That's all right.
That was
This
a
would be this because
Yeah, no.
there's two of these that have to one bottom one on top. So
Number
be
2
only a
might
single
not
one.
be a
That's
ketone.
it's gotta be equal.
Yeah, I think number 2 is an ether. Number 2 is an ether.